Okay, so here is a continuation of class number 5. This is video 4. We're going to talk about rigid body rotation when it comes to generating a free surface in a liquid, right? And we're just going to deal with a cylindrical body here, but it's a good opportunity to look at how that general equation can be applied in another way to another scenario right here. So here's our general equation where we have the pressure gradient it is going to be related to acceleration right here. And so really what we're talking about is a spinning thing of liquid. So first off, we need to change the coordinates to cylindrical coordinates. Cylindrical coordinates usually deal with, we have a something that looks like this right here. So I'm going to rewrite out, I'll just write out. Here's the pressure distribution can be described as having dP, d, del P, del R now. So we'll have a radial component in cylindrical coordinates. There's a hat, and there's our unit vector. And here is, now we'll have a d theta right here. So we'll have an angular one in cylindrical coordinates. Remember, cylindrical coordinates are like polar coordinates, except that now we have just a straight, we have another dimension, which is usually just in like the z-axis. So we have the same dz, e, we'll call it z right here, but often this is k, right? Remember, that's, for whatever reason, sometimes we will use e's, but other times for rectangular we'll use I, j, and k. So remember from dynamics that the acceleration can be broken down into at least polar would be r double dot minus r. We'll call it theta dot squared here, but we're quickly going to say theta dot is the same thing as lowercase omega, right? So it just means the rotational angular acceleration. A in the theta, sometimes called the transverse direction, is r theta double dot plus 2 r dot theta dot. You might remember that that's the Coriolis acceleration. And then we'll have, of course, just the acceleration in the z direction. But if we're dealing with something that's steady, and even though it's accelerating, that doesn't mean it could have like uniform acceleration. It's only spinning. So a steady spin means that we won't accelerate in the radial direction. And then we have a steady spin, so this is going to be 0. And also r dot is going to be 0, right? So we're going to be spinning the liquid, but none of the particles are moving outwards. So that means that's why the r dot and r double dot are 0, and we're spinning at a constant rate, omega, which is the same thing as theta dot right there. So that stays in, and then nothing moving in the z direction, so that's 0 right there. So if you rewrote all these things in gradient in the gradients forms that we had up for here, right? What we'd find, we get del P del R is going to be equal to, now this is no longer negative because that was negative, and that's negative up here, up above. So that's supposed to be a del. We have the density times r theta dot squared. And once again, I could make that omega squared instead. No problem. And then here, well, nothing changes in the theta direction, so it's going to be 0. And then we still have a pressure gradient in the z direction that's based on gamma right there, right? So because we still have pressure increasing as we go downwards. So what happens is we end up having these uniform, like when we go to integrate this, we get uniform lines of pressure. And more importantly to us, we have a free surface that kind of makes a parabola, interestingly enough. And if we want to get into the mathy stuff right there, we can apply the chain rule once again, right up to here. And okay, so we're only going to deal with the r and the z because remember the theta went away. And we could substitute back in what those gradients were, right? This gradient and that gradient up above. And when we say, okay, let's say that for a constant z, we could have this distribution here, and therefore we could set this right here as our conclusion, right? That's supposed to be it. I think that's supposed to be a density, right? I think that's supposed to be density, I think. Well, no. P is dP is constant, therefore P is constant. So I think, I guess P is constant. And so we're just looking for lines of constant pressure. That's what we're trying to do. Now, if we integrate this for a free surface, right, which is quite often what we're really looking for, we could just put this thing around and we could go dz is equal to r omega squared. You'll notice, so we made the transition from theta dot to omega at some point. And divide by g. I just wrote a row when I meant g. Okay. And then dr, and then integrate this, right? And if we do, we get a free surface equation. We'll get a constant of integration, but here we'll get z is omega squared r squared, right? Because we had r here, but we're integrating against r. And then I guess with we could say we're going to go from like the original or the bottom. I guess we're going to go from the bottom of the thing. So we'll see that in a second. But 2g, and then we're going to add in hc. And what we mean by hc is the bottom of the thing right here. So this is hc. In my other book where this figure came from, it was HO, but we're going to call it HC. Now, noteworthy, when we go to like try to find the volume of stuff, so this is close to being the same equation that's represented in the book. They have it in a bunch of different things. Yeah, I think this is like equation, call it 357 in the book. This matches up, sure. And in our book single. But when you're doing a differential problems, when you're doing something with a cylindrical one, it's often good to have little tiny cylindrical rings as our means of doing the integration. So, well, first off, let's take a look at about the initial total volume. We can just find that by taking the area. So here's the initial volume. By the way, the initial volume has to equal the final volume because of the conservation of mass and because of constant density. So the volume in the beginning has to equal the volume when it starts. So we'll say that it's going to be pi, and let's use the radius, and the capital R means it's the total external radius, right? This is the outside radius squared, and I decided this is going to be h is going to be the initial height. So here's the outside radius, and here's the initial height, and this is going to be the non-spinning volume, is what we just found. But an incremental volume that we would find from this right here, we'd have little tiny drs, right? We'll have the radius where that little r, where that ring is, and it could be the inside, the outside radius. It doesn't matter because it's such a small little thing, so it doesn't really matter whether you're talking about the inside, the outside. You talk about the average, it doesn't matter, just r, right? So we would have, let's say dv is going to be equal to 2 pi r, because that's the circumference, and here's the height, but here is the thickness of the ring, that dr. So we can integrate this knowing how r is related here. R is a function of height, and instead of me just integrating it, I decided to get lazy and said, well, the volume that we would find when spinning the thing is going to be equal to pi big R squared right here. So yeah, and I think we want to go. That's is that the big RO? I think I should make it big RO. I guess it doesn't matter. So I don't know if I really want to make that R. I just want to say that this was the outside radius of the thing. But I think this is also the outside radius. Times omega squared big R squared divided by 4G plus HC, right? And so where HC is going to be the bottom. This is the bottom of the container, right? So that this goes to right here, the bottom of the piece. So, and then lastly, I already said that, like, if M O is equal to M1, right, because of constant mass, and density is constant, right? So conservation of mass, constant density, then V is constant. And I could have just wrote that if M is constant. I don't know why I went MO and M1, but it's still true. So I think I have enough time to do the example here. It's not a long example. It's not complicated. And I don't think it's too terribly difficult. So we have this open 2-foot diameter container. I'm not going to ask about that right there, so let's get rid of that. And so this thing is open at the top, and the tank contains water to a depth of 3 feet to start with. And when at rest, if the tank is rotated about its vertical axis with an angular velocity of 100 RPM, revolutions per minute, what is the minimum height of the tank walls to prevent water from spilling out? Okay, so we need to find this. That's what we're out to get. Let's start out with changing the units of our 180 RPM by multiply them by 2 pi radius per revolution, right? Yep, so that's fine because we're going to get rid of revolutions. And then divide by 60 seconds per minute. So now we're going to get it into radians per second, 18.85 radians per second. The initial volume, which is going to be the final volume, is going to be the area times the height. So pi over 4. They gave us the diameter, so I'm going to stick with the diameter here. Times whatever I said it was going to be, right? It's going to be, I think I called it HO, the original height. So pi over 4, and the diameter is 2 squared, and the height is 3. And do we do okay? Yep. I think we're just multiplying pi by 3 for that, right? So 9.425 cubic feet is what we have. And so we want to set this equal to what we just got a minute ago, right? So the volume was going to be pi r squared omega squared r squared over 4g plus hc. And what that's going to do is going to give us HC. That's what we kind of needed, right? So we need HC to find out what maximum height is going to be. So we say 9.425 is equal to pi. Now the radius is 1 because the diameter is 2, right? Squared, kind of boring. And then omega squared, 18.85 squared. Times the radius squared, divided by 4, and then also apply gravity. And now that we're in feet, so we use 32.2, and then we add in HC. And from this, we'll be able to get what HC is. Throwing some numbers in there, 0.2413. So that's going to be the bottom height, right? So here, so if the free surface has an equation that can be found from Z is equal to omega squared r squared divided by 2g plus h. You'll recall that came from right here, right? That's how the free surface, so this is where the free surface is located, and that should be HC, I believe. I think I said, yeah, that's HC. So we're able to figure out how high the wall has to be by taking omega squared, or 18.85, square it, the radius of the thing, and this is the radius anywhere, but it's also going to be the radius at the outside, and divided by 2, divided by 32.2, but add in that initial height, and that's what we just got. That's why we got it. And we end up finding that the answer here is 5.759 feet. And so in a similar way, the maximum or the minimum, we should say the minimum height that we have to have. The minimum height that we have to have has to be 5.76 feet in order for this thing not to start spilling out. So I'm close to my 15-minute mark. And so this is the last example, last part of class number 5. And thank you for paying attention.